Welcome everyone to the second Rothschild seminar talk by Bernhard Keller. Before we start with the talk, I would like to mention that the notes from last week's talk, as well as the video, can be found on the Isaac Newton Institute webpage. If you go to the Cluster Algebra and Representation Theory program, if you scroll down, there's a schedule of seminars and talks, and next to the entry of the talk is a link to the notes, and or maybe if you is a link to the video, and then if you click on the talk, then you will find a link to the notes. Excellent. Okay, so the second talk by Bernhard on cluster algebras with coefficients and Higgs categories.
Thank you very much. I have also put a link to the notes of both the first and the second lecture into the chat. I hope the link works. If not, please let me know. So let me share my screen. Yes, here it is. Yes, let me start with a quick reminder of what we saw last week. We start with an ice quiver, so it's a quiver without loops nor two cycles, which has a frozen subquiver, F, usually drawn in blue. And then there are three cluster algebras associated with this ice quiver. The cluster algebras, cluster algebra with non-invertible coefficients. So it's a cluster algebra over the polynomial algebra in the coefficients. Then we can take the cluster algebra with invertible coefficients, which is a cluster algebra over the Laurent polynomial algebra in the coefficients. And then, well, we can specialize the coefficients to 1, and then we get the corresponding cluster algebra without coefficients. So we have this commutative triangle of cluster algebras. And at the level of categories, when our cluster algebra has a Frobenius categorification, then we have a nice lift of this commutative triangle, namely the cluster algebra with non-invertible coefficients corresponds to the Frobenius category itself. Then I tried to argue that the localized cluster algebra with invertible coefficients actually should correspond to the derived category of the Frobenius category, which is triangulated, and then the corresponding cluster algebra without coefficients would correspond to the stable category of the Frobenius category. And so this commutative triangle of cluster algebras would correspond to this classical commutative triangle of categories. Yes, we have the inclusion of E into its derived category, which maps each object to the corresponding complex concentrated in degree 0. And then we also know that we have a canonical triangle functor from the derived category to the stable category, such that this becomes a commutative triangle, where this is just the projection from E to the stable category. The stable category, remember, is the quotient of the Frobenius category by the ideal of morphisms factoring through a projective injective, the projective injectives corresponding to the coefficients. So here, this is precisely the process of killing all coefficients. And now Frobenius categorifications are very nice, but they only exist for a relatively restricted class of quivers. And so the aim is to before that, yes, I mean, when we speak about categorification, we need a decategorification map. And last time we saw that there is such a map, which makes, for example, this square commutative. And now the aim is to generalize all of this to a setting where we have many more examples. In particular, principal coefficients will always be possible. And that is, this new type of categorification is called Higgs categorification. And here, instead of a Frobenius category, we will have a Frobenius X triangulated category instead of a Frobenius exact category in the sense of Kurlan. We will have a Frobenius X triangulated category in the sense of Nakaoka and Pallu. Then this category will sit inside the relative cluster category, which plays the role of the derived category in the Frobenius setting. It is triangulated. And then we have a projection to a triangulated category, which is at the same time the classical amio cluster category associated with this quiver with potential, and also the stable category of this Frobenius X triangulated category. So we have not yet seen this, and one of the aims today is to define these categories. And then next time we will also see that we have analogous categorification maps in this more general situation. Okay, so now the plan for this lecture is as follows. So first of all, I would like to complete the picture which I started last time and show you how we can categorify quasi-cluster morphisms in the Frobenius case using the derived category. And then the main part is going to be the construction of the relative cluster category in the Higgs category. It's a generalization of Amio's classical construction. We will see examples from Dinkin quivers, which will allow us to see precisely what is going on. And then we will introduce a bit more structure into the picture. There is, instead of having, well, in the classical case, we have Calabi-Yau DG algebras. And here, instead of Calabi-Yau DG algebras, we will have Calabi-Yau morphisms of DG algebras, the so-called Ginzburg morphism. And this will allow us, this will lead to a relative Calabi-Yau property, which will allow us to compute the corresponding exchange matrices. And then in the final lecture next week, I will speak about mutations, decategorification, and braid group actions in this setup. Okay, so let me start with categorification of quasi-cluster morphisms in the Frobenius case. We have already seen an example last time. So let me now recall the notion of quasi-cluster morphism after Chris Fraser's definition from 2016. Let me fix an ice quiver with a frozen subquiver F. Yes, so our running example is this one of type A1. Yes, it's a very small but nevertheless instructive example. Then let's write n for the number of non-frozen vertices. We have, as usual, the n regular labeled tree.
Bernhard?
Yes.
Sorry, in the room here, in the seminar room, we cannot see the bottom line of your screen.
I see. Sorry. Can you? How far can you see now?
Now we can see well the line with just the n regular labeled tree with root.
You can only see until this.
Well, the below we can only see partially.
Ah, okay. Oh, that's important. Yes. Okay. Oh, that's yeah. Yes. Yes. So we have the n regular tree, and you can see this line. Yes, the AQ. No. No. Oh, that's really okay.
That was good.
Well, then now you can see AQ.
Yeah, although we'll have the opposite problem, but should I move it?
Maybe move
Or
the little
to the right.
screen up. Yeah.
Or make disappear the bar.
Mm-hmm. Okay, well, I will try to take that into account. Can you see both sides of the?
Yes.
Yes.
Yes. Okay. Okay. Yes. Yes. So we have the cluster algebra with invertible coefficients. Yes. So these quasi-cluster isomorphisms work well for invertible coefficients. And yes, so in our case, in our example, we have this algebra contained in this Laurent polynomial ring. Then we write P for the coefficient group, the group of Laurent monomials in the frozen variables. Then we write Q bar for the full subquiver on the non-frozen vertices. So we remove the frozen subquiver completely, and well, both the vertices, the arrows and all arrows incident with frozen vertices. So in this case, this just gives us the A1 quiver. Then associated with this, we have the algebra without coefficients. Then we write Qt for the mutated quiver associated with the vertex T of the n-regular tree, and Bijt for the corresponding coefficients of the exchange matrix. And then using the columns of the exchange matrix, we define the y hat variables. Yes, they are associated with the mutable, the non-frozen vertices of our quiver Q. For each non-frozen vertex, we have such a variable where the exponents are given by the corresponding column of the exchange matrix. And then Fraser defines a quasi-cluster morphism to be an algebra morphism which takes the coefficient group of the first cluster algebra to the coefficient group of the second cluster algebra, and such that cluster variables are mapped to cluster variables multiplied by elements of the coefficient group. So cluster variables do not necessarily go to cluster variables, but to cluster variables multiplied by some monomial in frozen variables. Okay, and then we get an induced morphism in the coefficient-free cluster algebras, and this should be an isomorphism which takes the initial seed of our first algebra to some seed of the second algebra with the same quiver Q. So the quiver should be preserved under phi bar. And okay, these are, well, quite natural conditions. I think then the last condition may seem a bit mysterious at first. Yes, so it concerns the y hat variables. So the y hat variable at the vertex at the root T0 should be taken to a y hat, to another y hat variable. And namely, well, we know which one it is if we look at the images of the corresponding cluster variables. And yes, and sorry, here there's an error. So it should be the cluster variable, of course, multiplied by some element of the coefficient group. Sorry, let me correct this. So here we have, so we write is contained in the coefficient group times the cluster variable. Okay, and a closely related notion called variation map is due to Van Zien in his paper on dual canonical basis. And well, here we have an example which we have already seen last time in detail, so let me not spend much time on it. So here we only have one non-frozen vertex corresponding to one y hat variable, just the ratio of the two coefficients. And then we have the corresponding cluster algebra without coefficients. And then you can check that this rule defines a quasi-cluster morphism. And this is an example which we have already seen last time. Okay, yes, so this is just to check that it is a quasi-cluster morphism. Now, how do we categorify it when we have a Frobenius categorification of our ice quiver Q? Well, let's look at the cluster algebra with non-invertible coefficients. So we assume that we have a Frobenius categorification, yes, So here's just a bit of notation. So we have our K-linear Krull-Schmidt-Frobenius category, whose associated stable category is Hom finite, and 2 Calabi-Yau, the dual of the space of morphisms from X to Y, is bifactorially isomorphic to the space of morphisms from Y to the second suspension of X. That's the Calabi-Yau condition. And then we assume that we have a basic cluster tilting object. We decompose it into indecomposables in such a way that the first n indecomposable factors correspond to the non-projective summands and the last m minus n to the projective ones. Then we have the associated ice quiver, so in which the frozen vertices should correspond to the projective indecomposable summands. This works also in the Hom infinite case. Yes, so the category E itself may be Hom infinite, but we make the necessary technical assumptions so that this ice quiver is well defined. And then, well, we assume that these data do define a Frobenius categorification in the sense of the first lecture. So in particular, we get a bijection between reachable rigid indecomposables up to isomorphism and cluster variables. And then, well, we assume that we have such a categorification for our quiver Q and an analogous categorification for another quiver Q prime. And then we define a quasi-cluster functor from the first categorification to the second categorification to be a triangle functor between the corresponding derived categories. Yes, so it's not a functor between the Frobenius categories, but a functor between the derived categories, which should satisfy conditions inspired from Fraser's conditions in the definition of a quasi-cluster morphism. So first of all, yes, the condition that the quasi-cluster morphisms should take the projective, should take the coefficient group to the coefficient group becomes this condition. The homotopy category of projectives of the first category should be taken to the homotopy category of projectives of the second category. As the first one is a subcategory of DBE and the second one a subcategory of DBE prime. And if we have this condition, then we have an induced functor. When we quotient by these categories, we get the stable categories. So we get an induced functor in the stable categories, which corresponds to the induced functor in the coefficient, so to the induced morphism in the coefficient-free cluster algebras. And well, in the case of cluster algebras, we require to have an isomorphism. Here we require that we have a triangle equivalence, and we had some, and we have to have some reachability condition. So the image of the cluster tilting object T, of course, has to be again a cluster tilting object because we have an equivalence, and this should be reachable from the given one. Okay. Now, to formulate the last condition, we define this category M double prime to be the additive, the closure under sums and summands of T double prime inside the second Frobenius category. And now the categorification of the third condition, remember the third condition was on the y hat variables. It was a bit mysterious, and it is categorified by this no less mysterious condition that the given triangle functor between the derived categories should lift to the level of the homotopy categories between the two cluster tilting subcategories M and M double prime. Okay, yes, so it's not immediately clear what this has to do with the y hat variables, but it is at least a sufficient condition. And then the theorem is that if we can find a decategorification of F in the sense that we can find such a commutative square, yes, these are the canonical cluster characters defined on the derived categories. If we can complete this square with some algebra morphism phi, then necessarily this phi is a quasi-cluster morphism. Yes, and if you go to the end of the notes, you should find an appendix, and in this appendix you can see what this last condition, this lifting condition, has to do with Fraser's condition on the preservation of the y-hat variables. Okay, then let's look at examples. So a typical example is the shift functor if we have the reachability condition. So if our cluster tilting object, the image of the cluster tilting object is reachable from the initial cluster tilting object, then the shift functor will be a quasi-cluster functor. Yes, you can easily check it, and it will be the categorification of the Donaldson-Thomas transformation, which will then in particular be well-defined, a well-defined rational transformation. And then, well, a very special case is the case where the triangle functor comes from an equivalence between Frobenius categories. Yes, so that's a very special case. So where we don't need to pass to the derived categories, we already have an equivalence at the level of Frobenius categories. And well, if we have such an equivalence which takes T again to a reachable cluster tilting object, then such an F is automatically a cluster functor. Yes, again, this is not completely obvious. Yes, you have to check the third condition, but it's not very hard either. Okay, yes. And then, well, the isoclasses of quasi-invertible quasi-cluster functors form a group. Yes, maybe, sorry, I forgot one condition. I should say, let's call them quasi-invertible, yeah, decategorifiable, which means that the morphism phi, the algebra morphism phi exists. So we can get our commutative square as here. Okay, then these form a group. I mean, if this phi exists, then of course it is completely determined by F. And so we get a group of autoequivalences, and this group of autoequivalences maps to the quasi-cluster automorphism group of our cluster algebra with invertible coefficients. And then one last remark. Suppose that we have two quasi-cluster functors. In fact, we can just assume that we have two triangle functors and assume that they satisfy some technical conditions. They should be continuous and algebraic. Well, that's the functors occurring in practice satisfy these conditions. Then if there are restrictions to the homotopy category of projectives are isomorphic, then the two functors are isomorphic. Yes, that's not hard to show. Yes, I mean, what is the reason? Yes, so we have these functors between these relatively big categories, and they are determined by their restriction to this subcategory of frozens, if you like. Why that? Well, if you take an arbitrary bounded complex over your Frobenius category, well, it is isomorphic in the right-bounded derived category to a right-bounded complex of projectives. Yes, just by taking projective resolutions. For example, if the object itself is concentrated in degree 0, then yeah, well, you can resolve it projectively, and so you get a quasi-isomorphism in the right-bounded derived category between the given object and this unbounded complex of projectives. Yes. So notice, well, if we try to do something analogous at the level of the cluster algebra or some completion of the cluster algebra, it would be a formula of this type. Yes, we would write an element, for example, a cluster variable. It would be written as an infinite alternating product of coefficients. Yes. So I haven't had the time to think about how to really make sense of this, what additional data, we need to make sense of this. But at the categorical level, it is, of course, very naive and classical, and it immediately implies that we have this property. The functors are determined by their restriction to the homotopy category of projectives. So if you like, the slogan would be that the functor is determined by its restriction to frozens, yes, which is a bit surprising, perhaps, if we put it like this. But notice that it will not work in general. This really depends on the fact that we have enough frozens, and which in our categorical setup means that E is a Frobenius category. Okay, so the frozen, I mean, the projectives, as you know, contain a lot of information about the Frobenius category. Yes. In many cases, the Frobenius category can be reconstructed from the projectives as the category of Goran's prime projective modules over P. And so this means that, a lot of information is actually encoded in the frozen part. And we will see more evidence for this also at the cluster algebra level in the next lecture. Are there questions so far? Okay, yeah. Please let me know if I forget about this problem of the lower part of the screen. Okay, then let me come to the construction of the relative cluster category and the Higgs category. So we take an isoquiver with frozen subquiver F. Yes, so this is the same example as we had a moment ago, again of type A1. And we choose a potential on our quiver Q. For example, here we could just take the potential A, B, C. And then we construct a generalized version of the Ginzburg algebra, the so-called relative Ginzburg algebra. Okay, so the construction is just a variation on the classical construction of the Ginzburg algebra associated to a quiver with potential. So what is this relative Ginzburg algebra? It's a differential graded completed path algebra. So the underlying graded algebra is just a completed graded path algebra, and it is endowed with a continuous differential. So let me just give you the construction in this example. So how does it work? Well, we start from our given quiver Q, and we add certain new arrows. Namely, for each non-frozen arrow, for example, B, we add a new arrow in the opposite direction, and this new arrow should have degree -1. So we keep all the given arrows and put them in degree 0, and we add new arrows, but only for the non-frozen arrows, and we put all these new arrows in degree -1. And then additionally, for each non-frozen vertex, so here we only have one non-frozen vertex, and for the non-frozen vertices, we add loops of degree -2. So the only difference with the classical case is that we do this only for the non-frozen part. In the classical case, we would add such loops for all the vertices and these arrows, these opposite arrows for all the arrows. Here we only do it for the non-frozen part. And then, well, as in the classical case, we take the completed path algebra of this new quiver, and we endow it with the unique continuous derivation, which, well, it takes the loops to the corresponding commutators between old and new arrows, and it takes the new arrows to the cyclic derivatives of the potential. And again, we do this wherever we can do it, and we can only do it for the new arrows corresponding to non-frozen arrows and the vertices and the non-frozen vertices, the loops at non-frozen vertices. Okay, and then as an exercise, as in the classical case, you can check that we still have a true differential. Its square vanishes. And then, well, as a hard exercise, you can show that in this example, the corresponding relative Ginzburg algebra is concentrated in degree 0. Yes. So if you try to show this directly by using the combinatorics of the paths and of the differential in this example, then that's a hard exercise. But fortunately, there are more efficient methods for proving such assertions. Well, so if you do it combinatorially, it's really not obvious. I mean, we were actually unable to do it with Yilin. But yeah, but there are other methods. So, and here H0 gamma, well, H0 gamma is given by this, as you easily check. Yes, you have to divide by these relations. And well, this is what you get in H0. And this is the endomorphism algebra of one of the two cluster tilting objects in the corresponding Frobenius category of modules over the preprojective algebra of type A2. Okay, and in general, if we go back to the general case, the relative Jacobian algebra is defined as the H0 of the relative Ginzburg algebra. So it is the completed path algebra of the given quiver modulo the closed ideal generated by all cyclic derivatives with respect to non-frozen arrows. And then we say that the ice quiver with potential is relative Jacobi finite if the relative Jacobi algebra is finite dimensional. Okay. Yes, so this relative Ginzburg algebra is the fundamental ingredient of everything that follows. So now starting from this DG algebra, we can form its derived category. Its objects are just differential graded right gamma modules. Yes, so they are just graded gamma modules endowed with a differential such that the Leibniz rule holds. Then inside we localize with respect to quasi-isomorphisms. Then inside we have the perfect derived category, which you can describe, for example, as the thick subcategory generated by the free module of rank 1. Yes, you take the free module and you close it up under shifts, extensions, and direct factors, and you get the perfect derived category. Then we have the perfectly valued derived category. So its objects are the DG modules M, which are perfect when you restrict them to the ground field. Yes, in other words, the homology of M is of finite total dimension. Yes, this is another way of saying the same thing. This was, yeah, previously, this category was often denoted by DFD of gamma. Yes, it's just a new name for the same category. The advantage of the new terminology is that it generalizes to ground rings which are not necessarily fields. And then inside PVD, we have, yes, by the way, here we also have an inclusion. And inside PVD, we have the subcategory of those modules with finite dimensional total homology, which are supported at the non-frozen vertices. So we assume that, yes. Yeah, so sorry, this is the associated representation. So this is just another notation for HPM times the idempotent EI, where I is let me see. Yeah, we require it to vanish for all. Sorry, let me see. We want it to be concentrated on the non-frozen part, so it vanishes on the frozen part. Sorry. Yes, so these are the DG modules concentrated on the non-frozen part and of total and whose homology is finite total dimension. And you can also describe it as the thick subcategory generated by the non-frozen simples. Yes, maybe that's easier to remember. Yes, so this SI is the simple module. Simple DG module associated to the vertex I. Okay, and so, well, in the classical case, when the frozen part is empty, you would take the full subcategory generated by all simples, and here you only take the non-frozen simples. And now, well, you would define the relative cluster category by dividing, instead of dividing by the whole category DFD or PVD, you just divide by this subcategory of DG modules with finite dimensional total homology and support it on the non-frozen part. Yes. Okay, so by definition, we have a short exact sequence of triangulated categories like this. And if the frozen part is empty, then we recover the classical definition by Claire Agnew of the cluster category associated to a quiver with potential. Okay, and then, well, what do we get in our example? If we take this example with the potential W equal to A, B, C, okay, well, we have to get a triangulated category. Which triangulated category do we get? Well, you can check that we get the derived category of the module category of the pre-projective algebra. Yes, so we get a derived category of some Frobenius category. So this is, I mean, what we would like to get is, in the end, what we would like to get is something like a Frobenius category, but here we get instead a derived category of a Frobenius category. So we also want to generalize actually the Frobenius category itself. Okay, and for this we need another step. Okay, and so this will be the Higgs category. So now to define the Higgs category, we first look at something which we call the fundamental domain or relative fundamental domain, perhaps more precisely. So this is the full subcategory of the perfect derived category, consisting of all cones over morphisms of objects in the additive closure of the free module of rank 1, such that the induced map in Hom gamma is surjective. In other words, yes, we take those morphisms between T1 and T0 such that any morphism from T1 to gamma extends along S. Yes. So gamma behaves, if you like an injective object where F would be a monomorphism. Yes. So we take these cones. This is, of course, the classical definition, except that we have to add this. Oh, sorry, and sorry, there's another error here. Yes, not all of gamma. I'm sorry. Gamma times I for all frozen vertices. Yes, I'm sorry. This is very important. I wrote this too quickly. Yes, so these objects, the frozen projectives behave like injectives with respect to the Fs which we use. Okay, and then we define the Higgs category as the essential image of this fundamental domain inside the relative cluster category. So essential image under the quotient functor. Yes, by definition, we have the quotient functor from the perfect derived category to the relative cluster category, and the Higgs category is the image of this relative fundamental domain under the quotient functor. Okay, are there questions or remarks concerning so far? No. Okay, and then by construction we we have this exact sequence. Inside the perfect derived category, we have this relative fundamental domain. Here we have its image, and then you can check that we get a k-linear equivalence between the relative fundamental domain and the Higgs category. And the fundamental domain, or the relative fundamental domain, becomes a hereditary extra-angulated category for the extra-angulated structure induced by this inclusion into a triangulated category. Okay, and so what do we get in our favorite example? Well, this diagram in this favorite example becomes this diagram. Yes, I hope you can see both diagrams on the screen in the room. If not, please.
You scroll down a little bit.
Can you see it?
You scroll down one line like that.
Like this?
Yes.
Okay. Thank you. Yes. So we compare this diagram with this diagram. So this diagram is the special case of this diagram for this quiver with ice quiver with potential. Yes. So the perfect derived category of the relative Ginzburg algebra becomes the homotopy category over the additive closure of the cluster tilting object in the module category of the preprojective algebra. Then, well, it's the relative cluster category becomes the derived category, and this functor is just induced by the inclusion of M into the module category. Okay, and then of course the kernel consists exactly of the bounded complexes over M, which are acyclic as complexes of modules. So these are the bounded complexes over M, which are acyclic, considered in the module category. Then inside here, the fundamental domain becomes the set of all monomorphisms between objects in the additive closure of the cluster tilting object. And this identifies as a k-linear category with the Higgs category. This is the Higgs category, which then identifies with the module category over the preprojective algebra. So this, I hope this gives some idea of what is going on in this construction. And now, so up to now, we have not made any finiteness assumptions, but now let's assume that our category, our ice quiver with potential, is relatively Jacobi finite. The relative Jacobi algebra is finite dimensional. Then you can show, well, Yilin Wu has shown that the Higgs category is closed under extensions in the relative cluster categories, which is not obvious from the outset. And then, well, it's an extension closed subcategory, so it has an induced extra-angulated structure, and for this structure it becomes a Frobenius extra-angulated category whose projective injectives are precisely the image of add of gamma E, sorry, look at, sorry, add of E gamma, yes, right modules. Add of E gamma, where E is the idempotent associated with the frozen part. Yes, so the frozen part yields us the projective injectives in this Frobenius extra-angulated category in the Higgs category. Okay, and then one can compute morphisms, one can compute extensions in the Higgs category, and well, this is, we get an exact sequence which generalizes a sequence due to Claire-Amiot. And in particular, we see that if we have no x1s in both directions between the two objects, then we have no x1s in the Higgs category. And so the image T of the free module of rank 1 in the Higgs category becomes a cluster tilting object. It is rigid, and for every object we have a conflation like this with T prime and T double prime in the additive closure of T. And finally, we can compute the endomorphism algebra. Yes, thanks to the equivalence induced by the quotient factor, we just get the Jacobian algebra. Okay, and so in particular, we see that every finite dimensional relative Jacobian algebra is the endomorphism algebra of a cluster tilting object in a stably two-color Frobenius X-triangulated category. And well, in the case of absolute Jacobian algebras, yes, there's a corresponding theorem due to Claire-Amiot. Yes, she showed that when we have some Jacobian algebra, it's always the endomorphism algebra of a cluster tilting object in a home-finite two-color triangulated category. And so here we have the corresponding statement, but now with coefficients. Yes, Claire-Amiot's theorem was without coefficients. Here we have coefficients, or in other words, we have non-zero projective injectives. And we have to replace the triangulated category used by Claire-Amiot by this X-triangulated category, namely the Higgs category. Okay, are there questions or remarks? Well, if that's not the case, let's generalize the small example which we have treated up to now. The generalization is quite natural and straightforward. So we take a Dynkin quiver, we look at the associated pre-projective algebra, then inside the model category of the pre-projective algebra, there's a canonical cluster tilting object constructed by Geiss-Leclerc-Schroeer in 2006. Its endomorphism algebra is always a frozen Jacobi algebra, as shown by Bruhat, Iyama, Wright, and Smith in 2008. For example, if we have a Dynkin quiver of type A4, then the quiver with potential, which yields the corresponding endomorphism algebra, is this one, yes, with this frozen part and the natural potential. And so associated now with this ice quiver with potential, we have a relative Ginzburg algebra. Then you can show that this relative Ginzburg algebra is actually concentrated in degree 0, and we can identify the ingredients of the defining diagram with the natural objects associated with the module category over the pre-projective algebra. So this, of course, is the direct generalization of the small example which we have used up to now.
Can I ask a question about this?
Yes, please.
Is F really these morphisms or the cones on these morphisms? I mean, it doesn't make that much difference.
Sorry, which letter is?
You repeat.
Sorry, I think no, I don't think I think I answered my own question. What I was asking is if F is the.
You mean this F? This F is the frozen part?
No, the curly F. I mean the fundamental domain. Sorry, the cone of a morphism of objects looks like a morphism of objects. That's why I was getting confused. Sorry, the question was about what curly F is, but now I understand.
What curly F is? Curly F is the cones over the morphisms small f. Yes, well, it specializes to these morphisms. Yes, in this case, and in general, it was the cones over morphisms f, where f goes from t prime to, well, let's say t double prime to t prime, and f, every morphism to every morphism from T double prime to some frozen projective extends along the morphism F.
I think Matt's question is just, you can also just think of that morphism as an element of gamma.
It is an object of per gamma, absolutely, yes. This curly F is a subcategory of per gamma, yes. Yes, so we have this lifting condition, and this is the definition of F, and it is a full, by definition, it's a full subcategory of per gamma, yes, and it becomes a hereditary extra-angulated subcategory of per gamma. Is it okay?
Sure, without the code.
Yes.
Yes.
Yes, yeah, it's fine. Thanks.
It's fine. Okay. Yes. Yes, okay, so we have seen this example. Yes. And now, yes, I think I have a few more minutes. Then I can say and can come to the Ginzburg morphism and the exchange matrices. So we take an ice quiver with potential, which is not necessarily Jacobi finite here. And we look at the two-dimensional Ginzburg algebra of the frozen part. So this, by definition, is again a completed differential graded path algebra. We take our given quiver, we add arrows in the opposite direction, now of degree 0, and we add loops for each vertex, now of degree -1, and we endow it with the differential, which takes the loops to the preprojective relations. So the homology in degree 0 of pi is the completed preprojective algebra. And then we have a canonical morphism of DG algebras from this preprojective algebra of dimension 2 to the relative Ginzburg algebra. It sends an arrow to the same arrow, now considered in Q. It sends the reverse arrow of a given arrow to the cyclic derivative of the potential, and it sends the loops to, well, these commutators associated with the vertices. And this is called the Ginzburg morphism. So let's look at it in our small running example. We have this example. Then the the two-dimensional Ginzburg algebra looks like this, with the red loops in degree -1 and the arrows in degree 0. And well, how does the morphism work? Well, C is taken to C, then the opposite arrow C star is taken to the cyclic derivative of the potential. So C star is taken to this composition, A composed with B. And then the loops are taken respectively to the corresponding commutators, which here simply reduce to compositions. Yes. Okay, yes, well, you have, of course, to check that this is compatible with the differential. And this, this Ginzburg morphism is really a central object. It carries what is called a canonical left relative three-Calabi-Yau structure in the sense of Bruhat and Dickerhoff from 2016. And this relative three-Calabi-Yau property generalizes the absolute three-Calabi-Yau property of the classical Ginzburg algebra. So if the frozen part is empty, then this theorem just tells us that the absolute Ginzburg algebra has a canonical left three-Calabi-Yau structure. In particular, it is bimodal three-Calabi-Yau. In a more general case, if our relative Ginzburg algebra is concentrated in degree 0, then this theorem has as a consequence that this relative Ginzburg algebra is internally bimodal three-Calabi-Yau with respect to the frozen idempotent, internally bimodal three-Calabi-Yau in the sense of Matthew Preslin's paper. The preprint is from 2015. Then maybe one last remark on this morphism. Yes, the morphism has this two-color algebra as a source, and therefore we have a braid group action on the source of the Ginzburg morphism, and this will turn out to be quite interesting in view of braid group actions on derived categories and on cluster algebras, and this is we will see that in the last lecture. And as a consequence of this Calabi-Yau property of the Ginzburg morphism, well, we get homological consequences for the category of perfectly valued modules over the relative Ginzburg algebra. We get, if you like, relative Calabi-Yau properties. So we take two such objects and we look at derived Hom over gamma on the one hand, and we look at derived Hom over the restrictions of these to pi. Yes, we have G, which goes from pi to gamma. So when we have a DG module over gamma, we can restrict it to pi, and this is what we do here. Just look at this. Yes, so we have this restriction morphism from morphisms over gamma to morphisms over pi. And then we can form the cone, and that gives us the first line. And now the relative Calabi-Yau property tells us that this first line is, in a certain sense, dual to the same line with arguments in the opposite direction. Yes, so in particular here in the middle, we get an isomorphism which is a consequence of the fact that pi is 2 Calabi-Yau. And if the restrictions of L or M to the frozen part vanish, then we get a 3 Calabi-Yau isomorphism. And in particular for empty frozen part, we get the classical 3 Calabi-Yau isomorphism. Okay, and we can use the, so we get control over the homological properties. And thanks to this, we can easily compute the Euler form between the simples over gamma, and what we find is this. So if one of the two is not frozen, then the Euler form gives us the difference of the number of errors from I to j and from j to I. And if both are frozen, then it gives us the opposite of the number of errors from j to I. Okay, well, if we do this computation in this example, we get this 3 by 3 matrix. Yes, in the case without coefficients, what we get in this way, of course, is the exchange matrix. And here we get, well, a generalized exchange matrix, generalized in a way which is perhaps a bit different from the ways which already appear in the literature. Yes, because this part, which is associated with the frozen part, yes, this part is neither symmetric nor anti-symmetric. It is, in fact, just the ordinary Euler matrix of this quiver, of this A2 quiver, of the frozen part, the ordinary Euler matrix of the Euler form. Well, if we use right modules, yes, if you use left modules, it will be the transpose of this matrix. And well, and for the rest, of course, for the non-frozen part, we get the ordinary exchange matrix of the non-frozen part. And here we get this, well, the rest here is also anti-symmetric, because if I or j are not frozen, then we have this anti-symmetric expression. And so, well, this is a bit different from what Fock and Contaro, for example, would do. They would use the anti-symmetrization with these half integers. But if we use anti-symmetrization, then we do lose a bit of information, because in general, it turns out that, well, if we mutate at frozens, then it can happen that we get frozen 2 cycles, and then the information contained in this matrix is no longer allows us to reconstruct the quiver. And we will see that next time. Thank you very much.
Okay, thank you very much for your talk, Bernhard.
Thank you very much.
Are there any questions? I think Karen is going to moderate in the room, or if you are on Zoom and have a question, please feel free to unmute yourself or write your question in the chat.
Questions in the room? Not the case right now.
I have a question.
Easy.
So in the two examples you showed, this relative Ginzburg algebra was concentrated in degree 0.
Yes.
And does that always happen?
No, it happens in nice cases. So it does happen in a surprisingly large number of examples. In particular, I mean, if maybe you remember, yes, so I looked at these examples coming from pre-projective algebras. This generalizes to the classes of examples considered by Buan, Iyama, Rayton, and Smith. So in a lot, which are also related to pre-projective algebra. So in a lot of examples, I mean, if well, we haven't proved this, but I think that if the Higgs category by chance is not just an X-triangulated category, but an exact category, and thus an exact Frobenius category, I think then it will be concentrated in degree 0. Right? I mean, this is, we haven't checked this, but I think it should be true. And so that explains why in many cases it is concentrated in degree 0. Yes, in contrast to the classical Ginzburg algebra, which is almost, which in the home finite case, it always has homology in infinitely many negative degrees. Yes.
And so what is then an example where it's not concentrated in degree 0?
For example, if you take principal coefficients, it will never be concentrated in degree 0.
Mm-hmm. Mm-hmm.
The converse of your statement is known, right? If gamma is concentrated in degree 0, then the Higgs category is Frobenius exact.
I think that's true. Yes. Yeah, I think that's true. Yeah, I mean, modulo suitable finiteness hypothesis, perhaps. Yes.
If it's Jacobi finite, yeah.
There seems, is there something in the chat?
I don't think. Okay, then I had one which I think you said, and I think I just probably missed it when you defined this quasi. I don't remember, quasi cluster functor, I think you called it.
Yes.
Then the second property that it sends the cluster tilting object to not
reachable. Yeah,
to reachable, so that sort of accounts for the coefficients that you get in the quasi cluster automorphism.
Yes, let me go back to the definition.
So the fact that it's not T prime, but it's just sort of reachable from T prime. Is
yes,
that...
yes. I mean, if you look at the definition of a quasi-cluster at the level of cluster algebras, let me share my screen. Well, here you have the definition. Yes, so it takes the coefficient group to the coefficient group, and if you look at what it induces after specialization of the coefficients to 1, then, well, it should take the seed to another seed, which has the same quiver, but which has some different cluster. Yes.
Okay.
Yes.
Let's see.
But this cluster is a cluster, so by definition of the cluster algebra, it is reachable from the initial seed, and that's why you have to ask for this image of the cluster tilting object to be a reachable cluster tilting object. Yes.
I see.
Yes.
And then how is the property A encoded?
The property, well, the property A says it takes coefficients to coefficients, and that means that it takes projectives to projectives, more precisely complexes of projectives to complexes of projectives.
Okay.
Yes. Yeah. Yeah. So this is the precise analog of taking coefficients to coefficients. This is the analog of taking a cluster to a cluster while preserving the quiver, and the quiver is of course preserved because we have a triangle equivalence. And then we have this slightly mysterious condition which lifts the slightly mysterious condition at the cluster algebra level.
Okay. Are there any other questions?
I have a question.
Yeah.
Okay, sorry. And does this work well if you take the twist on the Grassmannian?
I think so. I think so. Yes, yes, yes. I mean, the twist of the Grassmannian should definitely be an example. We haven't checked the details, but yeah, I'm more or less certain that yes, yes.
Okay.
Yes, yes, yes.
Other question in the room? No. Not right now.
Okay. Okay. If there are no more questions, then let's thank Bernhard again.
Thank you very much.
And then next week, we'll have the third talk at the same time, 3 o'clock UK time. And I think we'll post again the video and the notes on the webpage if you want to catch up. So thank you very much, Bernhard.
Thank you very much for the invitation and see you.
Okay, see you next week.
Bye-bye. See you next week.
Bye-bye.